Hi, everybody. My name is Lorphelin. I'm the head of developer advocacy and consulting at EventStore. What EventStore does is we provide services and maintain an open source database called EventStoreDB. And the thing is, this database kind of relates to event-driven architecture. So if we look at what I'm going to speak about, it's my mental simplified view of EDA and where it comes. Some problems I see with not EDA in itself, but the source systems, explain the state transition model, and then why storing events at the source is important. So my oversimplified view of EDA. A long time ago, we had a lot of systems and they all need to exchange information, interconnected, lots of connection, point-to-point connection. We all know that this is kind of an issue, especially when we look at how those systems actually connect to each other. They either connect to direct call to databases, API, exchange CSV files. So those are the typical problems that EDA has solved for us. The problem, of course, with exchanging information through direct connection to an operational database in systems is that we have this strong coupling at the data level, the data schema level. If you look at the API level, we have this runtime coupling happening. And if you look at more batch-oriented processing, like producing CSV files, we have end coupling at the schema level and coupling at the runtime level. Imagine that CSV file not being produced for a few days. So if you look at the type of systems those typically are, I might have a set of microservices all sharing the same database, some monolith existing that is calling other system, and one we tend to always forget is that BI and analytics are systems of their own, and they will typically need all the data we can provide at the application level, at the subsystem level. And this is where, EDA has been really helpful. What we are saying is, hey, we have all the services instead of point-to-point communication. Let's exchange messages between them. And typically, we have a broker, system send message, and they are distributed all over. Now, I'm using here the word broker loosely. It could be message queuing, it could be a streaming platform, it could be a lot of different systems, it could be SOLAS, Kafka, SQS, SNS, NQ series. I did use NQ series in the past. So that's what EDA solves for us. Loose coupling between our systems through messaging. And since we are talking about event-driven architecture, those messages are events. And what event mean is it's a significant change in state. Again, that's a broad discussion, that's a broad definition here. It's just a message which has been recorded and describes something that has happened in the source system, and other systems are interested. So where do I see problems with that? Is that typically, if you see how people are moving towards an EDA system, they want to produce events. And if I have a database, let's say in that system A, which is this set of microservices sharing a database, they will produce, or they will use an outbox pattern. So basically, when I'm mutating data in my data store, I will at the same time produce an event which is stored in the same database and which is then through some polling mechanism, for instance, is sent to the broker. And this works fine. The other way that I'm seeing people do that is using change data capture. So directly connecting to a database and looking at the transaction log of those database capturing that information and sending that to the broker. Both do yield some problem from my point of view. And if you look at the outbox pattern, what happens is that those systems are generating all those data, and it's kept at the source of the information, at the source database, but they will typically be fire and forget. So once that outbox has produced the outbox processing has sent the events, all those events will be removed from the source database. At the CDC level, what I'm seeing is the problem is that the promise of loose coupling is lost, because CDC typically looking at the transaction log of the source system is strongly coupled to the schema of that system, to the data schema of that system. So let's say if I have a relational database and a set of tables moving data through CDC, the schema of those tables and this data is exactly what is used by CDC, is exactly what is sent to the broker. And if I'm changing my source database, the schema, I have new requirements, I'm making a lot of changes. Well, the loose coupling is lost because the CDC part will typically have this, will need to cope with it. So two problems is we still have strong coupling at the schema level, and we forget information. We don't know why in the outbox pattern those events have been sent. They have just been sent. If you look now from all the type of systems, BI, this is exactly the same problem that BI has. BI typically has the same problems in their extract, transform, and load. Just as CDC, as soon as a schema changes, the ETL process breaks. As soon as, even if my BI system is capable of ingesting events, as soon as they are sent and processed, they are lost they cannot be reproduced, they are lost. Now, some broker, of course, can have like a retention policy saying, hey, I can keep my events or all this data for a few days. There are people who are using that for keeping all the data inside the broker. The problem there is that that's not the point of having retention policies at the broker level. The reason for the broker level retention is if my consuming system is down, then it can go back in time and have all the historical information from the last 7 days, for instance, being processed. Keeping everything at the broker level is also problematic because the systems, the team managing the system are losing control of the data. They can't do any change, and all those changes need to be accepted by the broker. Let's say I have a broker which can have a lot of partition and so on, and I need repartitioning. The more the system, the larger the company. Some other team will have to. Some other team will manage the broker or the CDC system, and the control of the data is lost and the history as well. So what I'm saying is that actually the problem is not CDC or Outbox or the problem or the broker itself. I'm saying that there is a fundamental problem on the way we store data at the application level. If you look at traditional database, and I love traditional database, I love relational database, I love document database, I love graph database, they do a really good job, but they keep only current state and they lose the context. They overwrite the existing data, and this leads to the same problem I just explained about ETL. As soon as you make a change, this change through the way we actually integrate in event-driven fashions are coming again, schema and loss of context. So what I'm saying again is change your data, the way you store the data at the source of the system with something like EventStore, which allows to keep events at the source. And we have events which are sent to my header pipeline. One thing to note is that the event at the source of the system, at the source system, are more granular and are not the same that are sent for integration purposes through the broker. I could have a lot of events in my source system which only triggered one or two on the broker side of things. So what is a state transition database? What is the state transition model? It's storing each individual state transition, so every mutation of my data at the application level as a series of events in sequence in an appender-only fashion. So events, again, are facts, they have types, they have some data. I will show a sample a bit later. The sequence means they are ordered. They are ordered and numbers. There's a global ordering, and we only append data. We don't ever overwrite data. This doesn't mean that we can't forget data. I can forget some events. I can delete some streams. I can delete some sequences. We need to support, especially for event-driven architecture, streaming, which allows application, which allows consumption in real time. Analytics love it. And we also need to be able to replay from any point in time. One thing about a state transition data model is that it is a more fundamental way of storing information, because I can take all those events and transform them into a relational model. I can transform them into a document model. I can transform them into a graph model. So at the database level, we have the state transition model. At the application level, that means using event sourcing. State transition are facts, events, and sequences are streams. For people who know event sourcing and streams might be more common words. So let's take a sample. This is my favorite domain, which was mass recruitment and selection. That was a time when I could say that my job was giving other people a job. And I'm oversimplifying the domain here, but let's say I have two important concepts: the concept of a selection, that's a selection process, and appointments, when people go and have an interview or some test that needs to be performed for that selection process. And a selection can be published. I can have enrollment started, enrollment ended, so people can actually apply for the job, or the selection can be paused or unpaused. Well, the same for appointment. I can enroll in an appointment and I can cancel an appointment. So those are in the data model when we store them streams with events of a specific type and some data in them, and then other streams. So if you take a sample, I could have a selection number 1 to 3, which is published, which is started, which is ended. Selection 3 to 1 concurrently is published, started, ended at different point in time. So events, again, the published, that's a business meaningful state transition. It has some information, the date that it's published, who published it, lots of information which is not shown here, and they have the sequence number. So selection 1, 2, 3 has event number 1, event number 2, event number 3. That's my sequence. And the same for my next selection. And we have different type of sequences. I have fine-grained sequences, fine-grained streams where I will append my data. And then I can look at this data in another way, think indexes, think views in relational model, where I could subscribe to everything that happens to all the selection type streams. So for instance, I could have published, and started, ended. And again, I have the sequence number. So there's a total ordering with 1, 2, 3, 4, 5, 6. One specific characteristic of that sequence is that that number needs to be gapless. Needs to be increasing, monotonically increasing, and gapless. This is important for distributed system. Go back. If I have state transition, I need at some point in time to be able to have current state. So if I have selection 1, 2, 3, I have published, the current state would be published, not started. A bit later, I have someone pushing a button or some automated system saying, now start the enrollment, or the enrollments are allowed to start. I have published, started, I have enrollment ended, and I have the more complex history of it. For instance, this one is published, which means my state is published, not started, enrollment started, published, started. And this is going to be interesting now. Post, publish, post, unpost, publish, started, post, publish, post, enrollment ended, ended. If you look at this from only the point of view of current state, which would be typically the green, so the green boxes, which would be typically stored in a document database or in a relational database, I have the problem that I have 2 times the same state in this history, but had different reason of existence. The history is completely different here. Here I'm post, but I was started before. Here I'm post, but I was unposed before. Even so, the sequence between those current state and think CDC now, if I'm seeing publish, started, post, started, post, and that's the only thing I'm seeing, there's no way I can understand why it came from started to post. The only way to know that is if we keep the actual state transition as a fact, as an event. So here it is post because it was unposed before. Here it is post because it was started before. That solves the CDC problem. Now, if you look at different selections, I have the same problem. Meaning, if I'm looking at the end state, publish, ended, those 2 states are exactly the same. There's no way I can make a difference between what happened in selection 1 to 3 or what happened in selection 3 to 1. If I'm keeping state transitions, I do have a different view of what happened at the business process level. Again, BI analytics love this kind of information. Another thing, so how can we put that in action into an EDA system? So I have my fine-grained events inside my system, number 1, number 2, number 3, 4, 5, 6, 7, and I want to publish events. I'm going to have a listener to all those events and decide at some point in time, oh, I'm seeing 1, I'm seeing 2, I'm seeing 3. Now I'm going to send, for some reason, might be the event type, might be some specific state transition that happened, and I'm going to send one specific message in the form of an event to my broker. And then 4 and 5, the same, I'm going to send an event. Number 6, 7, I'm going to send an event. So what's important to note here is that we have this concept of data on the inside and data on the outside. I have my events inside my system, inside my application, inside my microservices, inside my monolith, and everything that I'm sending outside of my system to the broker. So I'm gaining back here, actually, I'm gaining back that loose coupling and the choice of knowing what I'm going to send and when. So I'm not sending everything, and I have my decoupling between the schema inside my system and the schema of the messages that I'm sending outside of my system. There's another thing to note, I kind of hinted, is that when we consume those events, that sequence number is quite important. Because if you look at the consuming system, it will see I'm consuming event number 1, I'm consuming event number 2, 3, 4, 5, 6, 7. If those events goes to some broker that might not respect ordering, I might see 1, 2, 4, 3, 5, 6, 7. If you know that the source system is actually an ordered state transition system that has a sequence number, which is gaplets, monotically increasing, you can do out of order detection or missing message detection. In the second line here, if the consuming system is seeing 1, 2, 4, it can stop and say the last message that I saw was number 2, and now I'm seeing number 4. I probably missed number 3. Can fetch that message back, process number 3, then process the event or the message it just received, number 4, and then a bit later it will see number 3. And I know at that point in time, oh, I've processed event number 4, and now I'm seeing number 3. I will drop it on the floor because since I know the source system is gapless monotically increasing 1, 2, 3, 4, 5, 6, 7, if I'm seeing out of all the messages and that I had this way of picking missing messages, I can just skip number 3 and then go back into processing number 5, 6, 7 because I know it has already been processed. So this is one example of how this sequence number is really important. So in a nutshell, what I'm saying is that we should store at the application level each individual state transition as a series of events. Events have types, are part of a fine-grained entity stream, fine-grained stream. They should be kept in sequence in append-only fashion at the source of the system, at the database level. And that helps also solving that problem of CDC and outbox patterns where we forget data, CDC where we are still coupled to our source schema, and keep that data on the inside and data on the outside, which is the really powerful thing we can do with messaging and event-driven architecture, in my point of view. That was all I had to say. Thanks a lot.